Welcome to today's strategy session. I am absolutely thrilled to dive into this topic with you because we are going to completely unpack the Geometry Detectives Toolkit. Specifically, we're focusing on the rules of similarity and congruence. Now, if you are studying for your Cambridge Mathematics 0580 exams, or really any advanced math syllabus, these are two of the most absolutely fundamental concepts you will encounter. And honestly, taking the time to truly master them, to really understand how to orchestrate your mathematical arguments like a symphony conductor where every single step is in perfect harmony, well, it's going to completely change how you approach your past papers. You're going to start seeing these invisible rules silently governing shapes, maps, and scale models everywhere. So let's get our strategist hats on, settle in, and start analyzing how to guarantee those top marks. Okay, let's take a quick look at our roadmap for today. We're going from basic shape definitions all the way up to testing complex triangles. We've got 5 key areas to hit: similar versus congruent shapes, the scale factor rules, area and volume enlargements, rules for congruent triangles, and finally, testing for congruence. It's a beautifully logical progression, so let's just jump right in.
Section 1. Similar versus congruent shapes.
To start building our toolkit, we first need to understand the big picture difference between these two foundational concepts. It is entirely about the relationship between size and shape. I like to think of similarity like pinching and zooming on a photograph on your smartphone. The image looks the exact same, the angles haven't changed at all, but the side lengths are stretched out in perfect proportion. You're just scaling it up or down. Congruence, on the other hand, that is like using a rigid cookie cutter to get an exact, perfect match. You are stamping out a shape that is identical in both size and angles. There is absolutely no stretching allowed with congruence. It is a 100% absolute replica.
Now, the formal mathematical definition for similar polygons requires 2 very strict conditions. First, they must be equiangular, meaning their corresponding internal angles match exactly. Second, their corresponding sides must be in perfect proportion. But listen, here is a truly fantastic shortcut derived directly from our source material, and examiners love testing this. For triangles specifically, being equiangular automatically implies that the corresponding sides are in proportion, and vice versa. It's a special, locked-in property unique to triangles that makes our job as exam strategists a whole lot easier.
And this brilliantly illustrates a key logical rule right from the text. Let's really think about this for a second because it's a common trap. If you stamp out a perfect cookie-cutter copy, a completely congruent shape, it is mathematically also proportionally identical, right? That makes it similar. It just happens to have a scaling proportion of exactly 1:1. But zooming in on a shape, making it similar, means it is no longer the exact same size, so it completely loses its congruence. Basically, congruence is just similarity where the scale hasn't changed at all. Before we continue and look at how the math actually works, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, Section 2. The scale factor rules.
Now that we have our definitions locked down, let's see how similarity actually scales mathematically in one dimension. This is where we put real numbers to that pinch and zoom idea. The crucial point here is that if you divide a side length of your new, enlarged shape by its corresponding original side length, you get k. That is your scale factor. For instance, if a side goes from 5 centimeters up to 15 centimeters, your scale factor k is simply 15 divided by 5, which equals 3. Everything in that shape has been tripled.
But you have to remember, it is not just the outer perimeter sides that stretch. This is exactly where students lose marks. If your triangle sides scale by a factor of 2, the internal height of that triangle also scales perfectly by a factor of 2. Every single one-dimensional measurement inside that shape, the internal heights, the widths, the hidden diagonals you might draw in, they all stretch by the exact same scale factor, k.
Section 3. Area and volume enlargements.
Now, what is really fascinating here and absolutely vital for your exams is what happens when we escalate from one dimension, like a simple line or height, to 2 or 3 dimensions. You must memorize this rhythmic escalation. 1D length scales by k, 2D area scales by k squared, and 3D volume scales by cubed. Why? Well, imagine a basic square. If you double the length and double the width of that square, you aren't just doubling the total area, you are multiplying it by 2 times 2. You're making it 4 times bigger. If it's a 3D cubed, you double the length, the width, and the height. That's 2 times 2 times 2, making the volume 8 times larger. Before we apply this to a real problem, stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @ACExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, let's put this into practice, using a problem directly from the source material to test our new two-dimensional rule. We have hexagon A with an original area of 8 square centimeters, and it's being enlarged by a one-dimensional scale factor of 2.5. Take a split second to think about how you would orchestrate your mathematical argument to solve this.
Here is the perfect, foolproof method to ensure you never get this wrong on exam day. By systematically finding the area factor first, meaning literally taking that 2.5 and squaring it to get 6.25, we avoid the single most common trap in geometry. So many students just multiply the 8 square centimeters by the raw scale factor of 2.5. Don't do that. Instead, we multiply the original area by our new area factor of 6.25, giving us a completely correct final area of 50 square centimeters. Always, always find your area or volume factor first.
Section 4. Rules for congruent triangles.
Now we shift our toolkit back to congruence. Specifically, we're looking at the 5 unique fingerprints that prove 2 triangles are mathematically identical, exact replica matches. You do not need to check every single angle and every single side to prove a cookie-cutter match. Finding just one of these specific 3-point combinations guarantees the whole triangle is perfectly congruent. We have side, 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 angle, side, angle, 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 side, and finally RHS, which stands for right angle, hypotenuse, side. Let's look much closer at 2 of the most easily misunderstood ones.
I really want to emphasize the between part here for side angle side. The matching angle must literally be wedged right between the 2 matching sides to count as the SAS fingerprint. We formally call this the included angle. If the matching angle is just hanging out somewhere else on the triangle, unattached to those specific sides, SAS simply does not apply, and you cannot guarantee congruence.
Then we have RHS. This is your special tool reserved exclusively for right-angled triangles. It essentially uses a shortcut derived straight from Pythagoras' theorem. Think about it, because if you know the hypotenuse in one side of a right triangle, Pythagoras mathematically dictates exactly what that third side must be. This effectively turns RHS into a side-side-side proof in disguise. It's an incredibly powerful rule to keep in your back pocket when you see right angles on your paper.
Section 5. Testing for congruence.
Let's see how this builds into solving real geometric mysteries when examiners are intentionally trying to trick you. Here is a classic scenario from the text that tests your attention to detail. 2 triangles both have sides of 4 centimeters and 6 centimeters and an angle of 40 degrees. Are they definitely congruent? At first glance, you might think, well, I have 2 sides and an angle mapped out perfectly, so it must be an exact match, right? It looks like it should trigger our SAS rule immediately.
Absolutely not. The answer is a resounding no, and the source material strongly warns us about this specific trap. Without that 40-degree angle being specifically included or securely wedged between the 4-centimeter and 6-centimeter sides, you could actually draw 2 completely different triangles that both meet those basic criteria. This is known in advanced geometry as the ambiguous case. Because the angle isn't secured between the known sides, it entirely fails the side-angle-side congruence test.
So whenever you face a congruence problem, you need to build a mental habit of using this simple 3-step survival checklist. First, carefully map your knowns on the diagram. Write them out. Second, check if the shape has been rotated or reflected, because congruent shapes can absolutely be flipped upside down or spun around and they're still perfectly congruent. And finally, confidently match your mapped points against our 5 distinct fingerprints to ensure you aren't being tricked by an ambiguous angle.
Before we wrap up today's session, I want to leave you with this provocative true or false question drawn straight from the text to test your ultimate understanding of everything we've covered today. Take a moment, think like an examiner. All equilateral triangles are congruent. True or false?
It is false, because an equilateral triangle's angles are always exactly 60 degrees. They are always equiangular, meaning they are always completely similar. They have the exact same shape. But unless they share a specific identical side length, they aren't the same size. Which beautifully brings us right back to the very first rule in our geometry toolkit today. Similarity is about proportion, while congruence is about exact replication. Students who implement these specific mathematical strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. So here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams _IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep analyzing those shapes, and I'll catch you in the next strategy session.